Is Professor Peter Stephan from TU Darmstadt. Professor Stephan is a globally renowned expert in thermodynamics and heat transfer, currently serving as a full professor and vice president of TU Darmstadt. Professor Stephan obtained his PhD in the University of Stuttgart, where he specialized in energy engineering while contributing as a Marie Curie Fellow at the Joint Research Center of European Commission in Italy. His research spanned multiphase heat transfer, interfacial phenomena, spray cooling, heat pipes, and advanced heat exchangers. A prolific scholar, Professor Stephan has authored over 300 peer-reviewed publications, contributed to the Median Heat Atlas as an editor-in-chief, and supervised more than 50 masters and 7 doctoral theses. His contributions have earned him the prestigious accolades, including the Nikiyama Memorial Award and the VDM Medal. He will present on microrear formation and local heat transfer during nuclear drawing. Let's invite Professor Peter Stephan to begin the session.
Thank you very much. Yeah, well, welcome also from my side. I'm very happy to be here, and I thank specifically Ari Kotameta for inviting me here. I think it's my third time here at IIT Multiphase, and I must enjoy the science and the campus too. Thank you very much. Yeah, I will start. We saw application-oriented talk, the first talk. Now I will pick up some of the application-oriented technology, but I will go deep into basic science too. So you saw the topic of my talk, the title of my talk, and here you see some cool and flow boiling applications. Of course, as we saw in electronic cooling, also in space applications. Of course, power and refrigeration cycles and process engineering. And this is a typical cool boiling sketch, typical flow boiling sketch. What you see here is bubbles, vapor bubbles created, nucleated at a heated wall, and then either moved just according to the flow because there's a pump behind, or without a pump in a gravity field. They will rise due to gravitational forces. In non-gravitational field, they will not rise, but we will hear also talks about that from Atze Zilaf on the second day, or on this afternoon, I think, because we also had some space experiments. This is the typical Nikiyama curve. So the Nikiyama curve shows basically the performance of a boiling device. Here, a pool boiling curve from water. And what you see here is surface heat flux versus the excess temperature. Excess temperature is the wall temperature minus the saturation temperature of the fluid at the relevant pressure. So you see here different regimes. A forced convection regime without boiling. Then the nuclear boiling regime, then a transition regime, and film boiling regime. Of course, you want to avoid film boiling because you have very high excess temperatures. So ideally, you're running your device in the nuclear boiling regime here. And here, this starts from the onset of nuclear boiling to the maximum heat flux of the critical heat flux. So from an application perspective, what we want to do, we want to shift the Nikiyama curve in the nuclear boiling regime to the upper left side. That means we want to increase the heat transfer coefficient because this is high heat transfer coefficient and low heat transfer coefficient. And we want to increase the maximum heat flux, so here, which we also call the critical heat flux. From a research perspective, what does that mean? What are our aims? So our specific aim, first of all, is understanding the interaction between wetting and local heat transport in the nuclear boiling regime. And I will show you with the next slides why this is, I think, quite important. It is important to develop reliable and accurate models or correlations. And it is, I think, also very important for the design of optimized wall surfaces. So many people are designing nano and microstructures to increase, just to shift this curve somehow. Yeah. But if we want really to make it, to shift the curve to the left and to the top, then we need to have more knowledge how to design these micro and nanostructures. I won't go into the design of these nano and microstructures today, but I just want to give you an idea what is behind that. related to the wetting and local heat transfer. So, of course, what is influencing this Nukiyama curve or the performance of a boiling device is the heater material, it's the fluid, and it's the process itself. So, heater means the material of the heater, either copper, steel, or aluminium, whatever. And what's behind that are the material properties like heat conductivity, density, and so on. And the surface design, the geometry, the application, you might have tubes or flat surfaces, or thin surfaces, and the structure, either roughness or porosity, might play an important role. Fluid, of course, is important, so density, viscosity, surface tension is very important for boiling. And then process parameters such as pressure and heat flux and so on. So, for example, with pressure, of course, if you decrease pressure, then the bubbles are much bigger, in the boiling. There are probably 10 or more imperial correlations to calculate heat transfer coefficient, represented by the Nusselt number. Yeah. I should have taken maybe one from the VDI Heat Atlas. I took one from John Tomey's Wolverine Engineering Handbook. And what you see here in this empirical correlation is the following. You see here that the bubble departure diameter goes into the correlation here. And typically such a correlation has an uncertainty range of plus minus 35, sometimes 50, even 50%. For the fluids that they were tested for and for the pressure range that they were tested for. What you also see here, that this is not applicable to zero G applications or to low G applications, because G goes to 0, then the departure diameter goes to infinity, and then you can't use the correlation anymore. Okay. So for space applications, and what you also see, there are no wall properties except the macroscopic, static, and adiabatic contact angle, which is beta here. Yeah. No wall interaction, only fluid parameters, and that's the single parameter which has something to do with the wall. And that is insufficient, definitely insufficient. So what we can learn from that, comprehensive understanding of complex thermofluidic phenomena are still missing, even though there are decades of boiling research. Now this is again the Nukiyama curve, and here you see that you have a heated wall and then a growing vapor bubble. The nucleation is somewhere here. And when it's growing, you have a double boundary layer that is moving upwards. So the vapor bubble is, at least in the gravitational field, is going upwards. And then you have, of course, fluctuations of wall temperatures in the thermal boundary layer and at the wall. And we are interested now in how are these fluctuations, and specifically, as you can almost understand probably here, that there's a very high heat flux, local heat flux here in this contact line region. Okay? And this contact line is dynamically moving because it's moving outside, and then when the bubble starts to detach, it's moving inside again. So we are interested in the wall surface temperature, depending on the heat flux, and then we can calculate the heat transfer coefficient of the Nusselt number, for example. And again, I want to remember our aim is to shift the Nukiyama curve to the upper left side. That's my understanding. Now let's have a look on a growing vapor bubble in different configurations. This might be a pool boiling configuration. Pool boiling configuration, you will see in the next slides, we have to distinguish. Sometimes, depending on the growing velocity, you can have a thin film. Yeah. If the growing velocity is rather low compared to the evaporation rate, then you don't have a film microlayer creation. Yeah. Then you just have a moving contact line. Here you also have a moving contact line, but together with a film formation. If you have a micro-channel evaporation, as in some of the applications you showed, yeah, then you have typically a moving contact line situation here with the evaporation, and here a microlayer formation, yeah, if the bubble is pushed into that direction. And you can have this a similar thing in flow boiling configuration. Yeah, flow boiling configuration where you have a certain flow velocity in this direction. Maybe the bubble is flowing slightly in this direction, when it's detaching, it's moving that. So here you have different local configurations, local interactions between the wetting phenomena and the formation of microlayer or non-formation of microlayer. So de-wetting phenomena can be very different in these situations. How do they look like? And I took here the pool bonding application, and I show you how we think, and I will show in the next slides that it's true what we thought and what we found. That you can have this contact line evaporation, and with contact line evaporation, a typical heat flux profile, because you have very high heat fluxes, should have a peak here, a strong peak here. Low evaporation here, here slight evaporation, but here very strong local evaporation. And this profile should look quite different if you have a microlayer formation. You have the contact line here, the moving contact line here, but here very, very thin film, a couple of micrometers thick, and then you have a much stronger evaporation and the very thin film, which means a small heat resistance in this area. So the main question is, which regime is relevant in which situations? And I pose these questions because since for long, at least for one decade, there was a strong debate in science. Is it contact line evaporation or is it microlayer evaporation? And some people said it's always microlayer, and some people said it's always contact line. And I will show you that it can be both, depending on many main parameters. So which regime is relevant in which situations? And one, does microlayer form, and how different is the heat transport of these regimes, which is quantitatively shown here, but we are interested, of course, in quantitative measures. The idea of a controlled generic experiment that we have in our lab was the following. We thought we should move a heated plate, suck it out of a liquid pool, the heated plate, and then measure the temperature of the local temperature profile at the heated plate using an infrared technology. So and in an evaporation in a closed chamber where we have pure fluid, only vapor phase and liquid phase, and evaporation, and then a dry side on the back side of the heated plate. And then we would see the difference either in the contact line evaporation regime, when we move the plate and we expect contact line evaporation, or we expect with a de-wetting moving plate here a microlayer. And with the infrared camera, then we are able to see the temperature profile at the wall. I will show you in a minute how this this heated wall is designed. So we use infrared thermography because it has many advantages. Advantage is contactless measurement technique, of course, very high spatial and temporal resolution. And there are some disadvantages and challenges, of course. So we need a transparent optical path to the surface in the wavelength regime of the infrared camera. We need a surface with a well-defined radiation properties at the surface, so we coat it in this case. And of course, the calibration is not very simple. It needs to be pixel-wise in situ to reach the necessary accuracy. So calibration is a major thing if you have a moving target. I showed you in the beginning, our first idea was to have just a plate, and we pull out the plate from the liquid pool. But we found out that from an engineering perspective, this was extremely difficult and we couldn't do it. So at the end, we came up with a rotating plate. The typical size is like a large pizza, and on this large pizza, there's a small salami size. And this salami size is our heated sample. And this is here an open design. So we close the chamber, and then we can look through it here on the liquid level. And from the back side, with the infrared camera, we can observe the temperature profile here on this heated probe. And we run the experiment as follows. First, how does the heater module look like? We have an infrared transparent heater. It's a calcium chloride substrate, which is transparent in the infrared regime. we coat it with different layers. So the first is chromium nitrate emissivity layer, which has emissivity close to 1. And then a pure chromium heating layer, both of them around half a micrometer thickness. And then we attach electrodes to it for joule heating. And that's how we heat this stripe here. And we are able to observe the temperature profile on this heated plate. And the nice thing is that the thermal properties of this calcium fluoride glass are very, very similar to stainless steel. So using this infrared transparent calcium fluoride glass means we are close to an application of stainless steel. So we're not far away from application problems. And this here shows again a sketch. Now the chamber is closed. The liquid pool is here with the blue line. This is our sample, and we can move our sample by rotating the disc. However, when rotating and sealing and everything is much more easy in this rotating system than when we're moving linearly. However, this plate is almost moving linear because it's a small sample on a large plate. So if you tilt this plate, this movement here, of course, is a radial movement, according to this radius here. But if you move it only slightly, this is almost linear. The movement is almost. And we start the experiment by having the sample basically in the liquid part, and then turning the disc in this direction, and then the liquid moves, and we might create a microlayer, a film. We can measure the temperature from the backside, and then that's basically the end of the experiment. And of course, we can do de-wetting experiments and wetting experiments. Now, this is how the temperature profile now looks like. I will start the animation. This is before, so there's, and then we start the rotating disc. That means we move up the sample, and then the liquid will follow. What we see here is that's the x-axis in this direction, and we see here there's the contact line, there's the liquid pool, and there's our sample. You can see the top of our sample, and this is rather hot, and this is rather cold. And now we will move it. And you see the temperature, the heat flux profile here. And when we move it, we will see the following. Now, the liquid film is rising. We see here the temperature profile, and we see the recalculated heat flux profile. And thereby we can investigate this white line means there's the real contact line, but here now you see a film formation, a typical film formation profile. So that's how the experiment looks like. And we did a lot of experiments, of course, with different fluids and different pressures and different delta T, so different heat fluxes and so on. And we could see that depending on different parameters, which I will show in a minute, we have different temperature profiles. Either we are in the, I call it the contact line evaporation regime, where we only have a contact line, and then we have this typical peak heat flux. Or we are in the microlayer evaporation regime, and then we have the contact line here, and the film, a thin film here, a microlayer, and that means we have typically such a profile with a high heat flux, the spreaded region of this microlayer. Well, here it's really a peak, a single peak. And of course, this is much more effective concerning evaporation than this single peak. Now we were interested in when is contact line evaporation and when is microlayer evaporation. Here again you see different profiles, different heat flux profiles, and you see this for two fluids, for ethanol and FC72, perfluorohexane, a typical research fluid. And you see how this heat flux profile depends on the velocity of the de-wetting, velocity, so of the movement of the wall. And you see here, for example, for ethanol, up to about 20 millimeters per second, you see a single peak. That means you are in the contact line regime. If you increase the de-wetting velocity, then you suddenly jump and you come into with higher velocities, you come into the microlayer regime. With this large, rather large, it's in millimeters, That's a 4 millimeter long microlayer with high heat flux. And for FC72, it looks similar, basically similar, but of course different values of heat flux and so on. Now we try to make a regime map. And the regime map shows if you are in a microlayer regime with such a profile, typically, high heat flux profile, or in the contact line regime with a single peak. And we found out if we plotted the wall superheat is increasing, of course, with the heat flux that you apply. And here the dewetting velocity, because we can control the dewetting velocity with our rotating device. Yeah. So we really can control all the parameters, which of course you can't do in a real boiling application. And then we found we can distinguish that we are either we have no microlayer, that means we are on the contact line evaporation regime, or the green points we are on the microlayer regime. And there's a nice curve. Yeah, so you can see it's really two regimes, and you can distinguish these regimes by a critical velocity. And the critical velocity, dewetting velocity, depends on the heat flux, of course. So above this critical velocity, we are in the microlayer regime. Below this critical velocities, we are in the contact line regime. And the critical velocity depends on the superheat or on the heat flux. I take this plot again here. It's the same plot, and I try to qualitatively, this is quantitative data, qualitatively explain how the different changes. So if you have no heating, so you are in an isothermal case, no evaporation, and a static contact line, then this is this point. Yeah. No evaporation, no wall superheat, isothermal system, no dewetting velocity, zero, that means static. Then you are here, and then of course you have a classical contact line. So the microscopic contact line is the same as the macroscopic that you would measure with the contact angle. Now you increase a little bit the velocity. It's still without evaporation, 0 delta T, but you increase a little bit the velocity. And now, let's go back. That means simply you get into very classical dewetting situation, isothermal dewetting situation, and your contact angle becomes smaller. Yeah, if it is a little bit farther out. This is this point. Now, you increase it further, and that means you build a film. Landau-Levitch says you build a film. So you jump from the contact line to the microlayer regime without evaporation. Now we start everything with evaporation. We start again here at a static contact line. No moving plate, no moving system, but you increase wall superheat. If you increase wall superheat, you get a flux here, a flow in the liquid and evaporation here, and that means suddenly your contact angle is decreasing. So with delta T, contact angle is decreasing. Now we are here again, and now we start dewetting. So we go up into this situation where we have contact line evaporation. And if we further increase the velocity of the dewetting velocity, then again we build a microlayer. This is a really nice evaporating line. So we have to distinguish all these situations, and we are not able to transfer our knowledge from isothermal situations into boiling situations. And it's not only that the boiling situation or the velocity, the velocity is not only influencing the evaporation, but also the evaporation is influencing the dewetting situation. So it's a mutual interaction between both. Now, and we tried to find some correlations for this regime boundaries, because this I think is quite interesting for practical applications and for design. Of course, it's much better to be in the microlayer evaporation regime because you have local higher heat transfer than in the contact line. So we should know for our design purposes and where are we. So we found out that we can find a regime boundary nicely fit with the Jacobs number, and then the capillary number. The capillary number was specific capillary number for a reference case, and then the real case. And then, of course, we need some parameters to adapt. This here is for ethanol. So we found for ethanol these two parameters, and then it fits quite nicely. The delta T, of course, is proportional to the Jacobs number. So the heat flux that we apply, or the delta T, between wall temperature and saturation temperature, this is related directly to the Jacobs number. And the velocity, the de-wetting velocity, on the other hand, is directly related to the capillary number. So it's basically just here in dimensionless numbers, capillary number plus Jacobs number. And then we are either in the microlayer regime or in the contact regime. And we tried this type of correlation also for FC72, so for the spare fluid exam, this research fluid. And it's basically also this type of correlation fits very well. Of course, then the parameters here, the fitting parameters are different. It looks like this is quite universal. It looks like it's quite universal, such type of correlation to distinguish between the two regimes. Interestingly, if you quantify the total heat flux, at this heated plate versus the de-wetting velocity, and you see here for different delta T's, so the low delta T regime and the higher delta T regime. And the higher delta T, the higher can be the de-wetting velocity. This is the typical curve for the contact line evaporation regime, and this is the typical curve for the microlayer regime. So if you start increasing the de-wetting velocity with different with a certain wall temperature, you go up here, and then suddenly you jump. If you further increase the velocity of the capillary number, then you jump from the contact line evaporation regime to the microlayer regime. Then you get a much higher heat flux. So it's like a jump when you increase the velocity, jumping from the contact line evaporation regime. Suddenly microlayers form, and then you get and the total heat flux, of course, is somehow the integration of this curve. And of course, here with the microlayer, you see that you have a much higher heat flux, or overall heat flux, so a much higher evaporation rate for a certain given. And we also measured microlayer length and microlayer thickness. And this here also shows some interesting results. So the microlayer film length, this length here, L, it's increasing with the de-wetting velocity. That was expected, of course, and it's decreasing with wall superheat. That's also can be expected. The higher the wall superheat, the higher the evaporation rate, the shorter. Here we plotted. You see different delta T's. So for higher wall superheat compared, so 2.5 Kelvin to 4 Kelvin superheat, you see from 2.5 to 4 Kelvin superheat, the length is decreasing. And of course, it's a function of the de-wetting velocity. The higher the de-wetting velocity, the longer the microlayer. This is also a correlation that helps here. This correlation capillary number scales with the power of 5 divided by 3. So it seems to be rather universal. And the microlayer thickness delta here of the microlayer also scales quite nicely here. The capillary number to the power of 2 3. And you see that the thickness here is increasing with the velocity, and you see that again the thickness of the microlayer is decreasing here when we increase. This brings me to the end of my talk. Some key messages for you to take home. I would say that wetting and de-wetting, I showed only the de-wetting cases here. This means the contact line dynamics are strongly interacting with mass, momentum, and energy transport in the nuclear boiling regime. concerning the local heat flux near the contact line, we found out that there's an extremely high local heat flux and close to this moving contact line. So we should try to optimize specifically this situation. Local microscale phenomena affect even the macroscale fluid flow and heat transfer. So even though this contact line movement and local heat transfer is a very small scale, just inside even a smaller scale than the thickness of the thermal boundary layer, part of the thermal boundary layer. Nevertheless, it has a rather large difference on the overall evaporation rate. We have a massive number of different evaporation regimes near the contact line. There's a dynamic dewetting regime transition that can occur in the presence of evaporation. So a jump between microlayer evaporation, contact line evaporation. For water, we also did some investigations, preliminary investigations towards water. There we are mainly in the microlayer, more in the microlayer regime in typical parameter range, but also there must be a jump between these two regimes. And microlayer evaporation is more efficient than contact line evaporation. So if we design our nano and microstructures to improve the Nukiyama curve, to shift the Nukiyama curve to the upper left part, and we should do it in such a way that we get more microlayer situations instead of contact line evaporation situations. And with that, I would like to thank you for listening, and I would like to thank our sponsors. We have a collaborative research center on the interaction between transport and wetting processes in Darmstadt. I've been to visit this a couple of times. If you want to find more details, here are some two papers mentioned, and also a thesis mentioned of Kai Schweikert, who is available online on our library and our website. So you can find much more details of these things in these publications. Thank you very much.
Any questions?
Thank you. Very elegant experiment. So two questions. One is, what happens if you have a highly hydrophobic surface? Can you actually end up with a contact angle greater than 90 in this?
We didn't try. We actually didn't try because we have this chromium coating. It's very difficult to change the coating. We're working on changing the coating at the moment, but
in theory, would that always be a contact line evaporation? Do you think?
I'm not sure. It should be the contact line regime should be larger by means of the process parameters, velocity and so on.
And then you talked about designing a surface. So what sort of things? I mean, is it surface roughness, wettability? What do you think we could do to
this surface? This specific surface is very, very smooth. And at the moment we are trying. Axel is doing a lot of work in this direction. We are trying to apply different coatings on this infrared transparent glass, which with roughness, with microstructures, and I'm not sure about the outcome, but definitely if you have a super hydrophobic surface, then the liquid doesn't stick to the wall. So you should move the wall and you are always in the contact line regime. But for the typical applications, of course, for the boiling regimes, you need good wetting situations. If you want to reach high evaporation rates, you should avoid super hydrophobic surfaces.
So I have actually two short questions, but to do with the slide 30 and 31 near the end of the top group. And the first one was you gave us delta, the thickness of the microlayer, and the question was, how did you measure that? But my real question is, can you measure the contact angle?
We can measure.
If you can measure delta locally, you could measure that.
We can measure contact angle outside this experimental setup. We tried to visualize it through this small window from the side, but that's very difficult. So we measure it in a standard, but heated contact angle device.
But then you would be able to have basically dynamic contact angle models if you could, I mean, without heat transfer, just leave the heat transfer out for now and just do but the second question was on the 31, then that is 31, and you have this graph that the thickness changes with velocity. But the question is, with velocity, of course, the temperature, the heat flux change, the temperature in the thin film is changing. So
Yes.
is the thickness change just due to a viscosity change, maybe?
I doubt that.
Which you could do with the Landau-Levitch.
Yeah,
You would immediately see that.
Yeah. It's well.
So what is the thickness change due to? I would think it's due to viscosity, but what's it due to then?
No, it's not only viscosity, because then Landau-Levitch would fit. Yeah, and it's similar like Landau-Levitch.
If you took the right viscosity.
Yeah. If you took the right
You need the heat flux, and you have the heat flux.
But these delta T's differences, the temperature differences are so small. So I would say it's not possible that this is.
Okay, but then the question remains: why does the thickness change with velocity?
Because you have different evaporation rates. Much higher evaporation rate with higher
So
delta T.
you're simply evaporating at a faster.
You're
So
evaporating
it's mass
faster.
flux.
Yeah, it's mass flux.
Okay.
Mass or heat flux.
Okay.
A couple of questions. First is that you see the length of the microlayer changes when your retraction velocity changes, right? Is there upper limit to the length of the microlayer region? Or does it change? Like,
Go fast.
as fast as
I'm not sure, because our parameter range, of course, is limited. Yeah. Bending velocity is limited, the size of our sample is limited. Yeah. So I would guess that you can reach much higher lengths, in a different setup. Yeah. But our setup in this case is limited.
Another question is like, did you look at it theoretically? Like you have like evaporation rate and heat flux that you're measuring, but theoretically, did you try to use any model to look at the rate of evaporation?
Yeah.
That is always like a question.
Yeah, we do that specifically for the contact line evaporation regime, and we will have a presentation also here. Johannes Kind will show.
Do you use the Schrage equation or do you use something different?
Pardon?
Do you use the Schrage equation or do you
Yeah, we use the Schrage equation in our model. So we have a sub-model for this contact line area, and then a CFD model for the larger area of the blowing bubble. And then we combine this, we call it microregion model with Schrage's equation and heat resistance at the interface. We combine it with the open foam as a CFD tool.
Just one more question. So this is all in the saturated environment.
This is all in a saturated,
Let's say
fully.
we take it to ambient.
Exactly.
And the same tests. Do you think the same findings are going to hold good?
No, no. I think it will change because then you get some mass resistances. Yeah, diffusion will play a role in the gas phase. Yeah, because it's a mixed phase. Yeah, and this will change. But if you look to the pool boiling application or flow boiling application, then it's pure vapor. Yeah. But I think it should be easier to make an experiment in a just air environment, instead of having it in a closed chamber. Yeah. So this was rather tricky to build a closed chamber with a controlled vapor environment. But of course, it's restricted in the parameter regime. But you're right, it will change because diffusion and mass flux. This will play a role.
Usually the experiments with pure vapor are more difficult, but the simulations with pure vapor are easier. So you need a more complex simulation tool for multi-component system, but it's more easier to build the experiment for.
Doesn't match.
I have a basic question. The blue region that you have indicated in that figure, so can we define something like an apparent contact angle there, or does it make sense to do that in a micro layer region?
I guess so. Yeah, I guess so. I tried to show it here, or it wasn't here.
Yeah.
I mean, you see here the different situations, and what you typically measure, is the macroscopic angle because you don't see all the details here. Yeah. But the microscopic angle will be somehow different. And of course, if you are in this regime here, yeah, okay, here you don't see something. Of course, also we see a contact line in the microlayer regime from our temperature profile. There's a contact line. Yeah, we saw it in this movie. Where was this movie? Ah, it's the wrong direction. Go back. Here, this movie. This movie you see here we marked with the white line the contact line. Yeah. And now you see the contact line is moving up. And the contact line is still there. Yeah, but you see also some oscillations here, you see some instabilities. Yeah, of course instabilities, you see everything, but you see here microlayer from here to there, then the contact line, it's oscillating, yeah, it's not, there are some instabilities too. Data that I showed later on the plots to distinguish was just an average. Yeah. Further questions?
In case of a superhydrophilic surface, let's say if you use, so then the liquid will first start moving off even without a velocity.
Yeah.
So in that case, what do you expect? And in your any of these relations, you don't have the weighting characteristics of the surface. So do you think that the universal relations that you obtain will also modify?
I think they will modify. Yeah, depending on the surface properties and on the static and dynamic isothermal contact. Yeah, I mean here we used I presented two different fluids, ethanol and FC72 on the same surface. Yeah, now we are trying to use different surfaces. Of course, the correlations and things and the regime boundaries they will be different. Yeah. But I hope and I'm pretty sure that the idea behind how to distinguish this will be real.
Professor Atul.
My presentation highly appreciate the idea of designing the experiment. However, I was wondering that what is the biggest of assumption, the way you are trying to correlate your experimental results with the theory. What is the biggest of assumptions and its justification? And second thing is, you are showing us a great promise that if, as an engineer, we are able to control the contact line velocity, we can get a sharp jump in heat flux or heat transfer coefficient. So, whether you have a afterthought that how we can engineer surface where we can have contact line velocity on demand.
You're not able to, that's very interesting, yeah, because at the end, this has to go into the application. And of course, we are not able to, that's why we build up this controlled experiment where we can really set the velocity. In a real boiling experiment, the velocity is first of all changing from 0 to plus 3 millimeters per second, yeah, to minus 3 millimeters per second, and this is fluctuating. Yeah. So you have all the different velocities in a boiling situations, but you can design the surface in such a way, yeah, that you as you saw that you are more, at least for the growing bubble situation, that you have the microlayer formation. And the microlayer formation has two advantages. The first advantage is that you get a high heat flux during the bubble growth rate. The second advantage is that when the bubble detaches, it's much more easy if you have this microlayer that you re-wet the surface. And re-wetting the surface very fast is very good for the for the maximum heat flux, to increase the critical heat flux. So that's why we should design the surfaces in such a way. But in a real boiling experiment, you go through all these situations.
So Peter, I also have a question. So the sketch that you're showing it's just an illustrative sketch, right? It's not a fit from the actual experiment.
This is from the actual experiment.
No, the sketch.
Ah,
that-
this sketch.
yeah.
No, this sketch.
Because otherwise you
No,
can
no, no,
also
this
measure
sketch-
the apparent contact
This
angle
sketch
from here.
is only design.
Design.
This is real experiment and this is real experiment. Yeah, this is experiment.
Any other questions from the participants?
Thank you very much.
Thank you, Professor Stephan. I request Professor Abdul Sharma to present.